Okay, so I'd refreshed my memory on pointers. I'd created a phase one C program which basically interpreted the instructions, and that's all it did, using pointers to functions. So I moved on to phase two, and phase two I decided that we probably needed some sort of interactive environment to allow me to work within the scope of the emulator, manipulate the memory within the emulator, display the registers and that kind of thing. So I think what I decided to do was write a CLI basically, and this is how it looks. So the first thing that happens when you move into the interactive CLI is it displays the 6502 registers as we've set up in the program. The A register, the X register, the Y register, the stack pointer, the program counter, and then the status register. And the status register, actually, it's not quite right. I've labelled it up slightly wrong in this version because I labelled it up as a sign bit, when in fact that should read the negative flag. It gets changed later on, but leave it alone for now. And the negative flag is set when the result of a calculation or a comparison results in a 2's complement negative. So basically bits, the high bits of the result is a 1, or we might do a video on that at some point. The overflow flag, that's quite a complicated beastie, but that's set if, for example, if you add two positive numbers and end up with a negative number, you will get an overflow, and there's the binary reason for that. It's to do with how the high bit is used. So the sign bit and the overflow bit go hand in hand. This bit is always bit 1. We discussed that way back. This is the break bit. That's an interesting one. In fact, I've been doing a bit of reading lately about the break bit, and I've made a mistake with the break command, but the break command isn't really used a lot, but we'll probably rectify that later on. This is the binary to decimal flag. So are you using binary to decimal? We're not going to use binary to decimal at all, probably ever, mainly because it's not something that interests me at all, and I was more interested in sort of putting some basic emulator code around the 6502, all the sort of binary to decimal stuff. I wasn't interested in, and I believe some of the consoles and things like that use a 6502, they don't use binary to decimal either. Anyway, but that's what that is. Then you've got the interrupt disable flag. Now this is an interesting one because this on first look seems to be a back to front flag, but it's not, because the word disable in interrupt disable is the most important thing. So if interrupts are disabled, then the flag is 1. If interrupts are not disabled, i.e. they are enabled, then the flag is 0. So you kind of have to remember that that isn't the interrupt flag, it's the interrupt disable flag. This is a 0 flag, and any calculation or comparison that results in a 0 will set this flag to 1. So 2 minus 2 equals 0 would set this flag. This is the carry flag, and any result of any comparison or any addition, subtraction, that results in a carry. Now in an addition, a carry is something that, for example, the accumulator is 8 bits, 1 byte, and therefore the maximum it can hold is a value of 255, which is all ones, or FF in hexadecimal. If you add something to something else, so let's say for example we had the value 250 to the value of 10, then the answer is 260. But the way that it works is that actually the value of 5 will end up going in here, and the carry flag will be set. So what the carry flag basically says is, I have just gone over the 255 mark because I can't hold anything else inside of the accumulator. Therefore, please add 255 to the value because I've just carried. So, what does this thing do? Well, I created a help command, and I created the help command for me because it's easy to forget what you're up to. So every time I add a command into the CLI, I add it into the help so that I can easily remember where I'm up to and what it does. So at the moment I can insert hexadecimal values into memory, I can display memory, and I can display the registers. So if we display the memory first, now I made a couple of mistakes here as well, and I rectified them later. And the mistake is that what I did was, first of all, I used the C notation for hexadecimal, and secondly, I didn't take hexadecimal as default. It became really tedious and boring to keep typing this 0x in all the time. So later on in a subsequent revision, and I can't remember which revision, I removed that from the CLI, and I moved on to just sort of being able to type the number directly, but we'll see that later on. The second thing that's a note is the fact that I don't display memory in a traditional column, rows and columns in this earlier versions, because I wanted to make it very easy to see exactly which memory location had exactly which values in it without having to count, mainly because I was doing this kind of coding late at night or in sort of obscure times, and it made life a bit more straightforward. That gets rectified at a very later version as well. So the insert routine, if we type I, it comes up with a basic command, and it's a basic help, and it says, oh, you didn't give me enough parameters and you have to give me a memory address and you have to give me a value. So let's insert something into 0xC000, and we'll insert A9 because we know from previous videos that A9 is akin to LDA for an immediate. So what that then means is that we actually need to put something into C001 as well, because the LDA needs a value. The LDA immediate needs a value, so we've now done that, and we can put 0x002, and we could oops, we can't do it that way. We have to insert 0x002, and we could put 60 in there, 60 hex, which is the value for RTS. So if we now do a list for the memory again, so if we do a list for those two, so the start address and the end address, you can see that it's displayed A9, but it's also displayed it as a decimal. It's displayed what's in position 1 is both hex and decimal, and funnily enough 4 is the same, and it's displayed hex and decimal there. So that's actually a very small program that set it up so that we can write opcodes and values and things into it. So that would actually read LDA 04 and then RTS, and that will allow us in the next incarnation of this video, of this emulator, to be able to start adding instructions and doing things with the instructions, and then therefore testing the instructions and making sure the instructions work correctly. The other thing to remember to know is that quit works, and once you've quit, then if you go back into the program, then you basically running a new version of the program, and a memory dump will give you what it did when you first ran it, which is basically an empty memory, because it reinitializes the memory on start of program. So that's just natural standard programming. So the other thing to note is I split the program into three files in this iteration. I moved all of the instructions into their own file. They're exactly the same as they were in the original version, in the fact that all they do is printf to the screen based upon what you pass through, and that's all they do. So there's no change to those apart from the fact that they're now in the new file. There's a few changes in here, in the fact that I was playing about with external variables. That all gets changed later because it isn't actually right. I was just playing about for my own use to refresh my memory on things like what extern does and how static variables work and things like that, and this was kind of how I Just my playing really, just as a refresh, it's not right and it gets changed. And there's absolutely no difference down here with the array of pointers to functions. So this is all exactly the same, and this doesn't actually change very much. It does change a little bit, but I'll come on to that in subsequent videos. But there's a reason for the changes. It doesn't. The structure of the array itself doesn't actually change. The biggest change is in here, which is the main C file. Again, it's all around writing the CLI, which we've just seen in action. First of all, I have to create a buffer, and the buffer is an input buffer. It just allows me to type characters in. The buffer size is 32, so I use this allocate memory to say, okay, please give me some buffer space, please. And I've also created an array of pointers there, which are the tokens. And the tokens are used as part of the built-in the standard library of string tok. And string tok is a tokenizer. There's a lot of information out there on the internet of how string tok works. I didn't bother writing my own string tokenizer because for this purpose, string tok does exactly what I need it to do. So what happens? Well, we print the colon to the screen. So we start a while loop, and we basically say while not quit. And the quit command is somewhere up here where I've set quit. There it is, quit equals 0. So while not quit, so if quit is still 0, keep going. And then you set up some variables, print the colon to the screen, then start getting the characters into the buffer. Then we tokenize them. And a quick overview of string tok. What it basically does is it takes a string, and what we do is we tell it that we want to tokenize on null. We want to change whatever, we want to change something to a null character, and in this case we want to change the space because that's what we've thrown in there. So we change the space to a null character. Okay, and it passes back an array of pointers, and I'll cover array of pointers I think in a different video. It's very simple construct, but the constructs within what we're trying to do are actually quite important. So then what it goes along and it says, okay, look, what did you type? Did you type a H in as the first letter of the first token? Did you type an I? Did you type an M, and so on? And then it does some validation on that, and it says, well, for an I, for example, which is an insert, I need at least 2 parameters, and therefore including the I or the insert. That means that there must be 3 words or 3 tokens passed in. So it says if J, which J was sort of set up here as part of this token count, if J is less than 3, then tell me what the usage is, and that's how we did it before, if you remember, on our I. So if you just press I and press return, it gives you that usage information, and it will do the same thing for M as well. And you can see that M's got a slightly different format, and you can see how that works. That works here. So there's the M. So it says if J is less than 2, then the usage followed by a tab is memory, and then the start address and the end address, followed by a new line character, which is there, followed by a tab, and then the second option that you've got, and that's precisely what you see here. So it shows you how you can use the routine. But if you've passed enough parameters into either one of these, then obviously the else clause of the if says, well, that bit wasn't true, so this bit is true, and therefore pass the tokens into this this function or this function. And inside of these functions, what we do is we take the tokens that were passed and we say that within pointers, within a pointer to a pointer or a pointer to an array or whatever, you can register them as almost like two-dimensional arrays. You can reference them rather as almost two-dimensional arrays, and that's what I'm doing here. So I'm basically saying if the second element, because bearing in mind C arrays start at 0, not 1, so therefore if the second element is an X, so when we typed in when we type in memory dump 0xC000 like that, then what it says is if that second character is an X, which it is in our example there, press return on that and it works. So it says if it's an X, then set the base to 16, so therefore we're working in hexadecimal. Else, if it's anything else, presume that we're working in base 10. And what that then does is we pass that into the str2l. I think it's string to long. So what it does is it takes the string that we've created, because if you think about what we've created as a token, it's not a number. It looks like a number on the screen, but it isn't. It's a load of characters. It's a C, it's a number 0, it's another number 0, and another number 0. But what we need to do is we need to get our program to pass that back as something else, and in this case we know that the first token is the address part because it is, right? And if there is another token, then the next token is the contents. Okay, and the contents is, sorry, am I looking at the wrong one? Sorry, I'm looking at insert here, not display, but it doesn't matter. So on the insert, for example, you've got you do insert and then 0xC000, and then you put in some contents, which we did before, which was A9. So what that basically says there now then is address and then contents. So there's your address, there's your contents. It converts both of those into an actual number rather than a string. And then using the array that we've already talked about in previous videos, we use the address part here as the index into the array and the contents as the value that we're going to put into the array. And it's as simple as that. And the display memory is somewhat similar, but because the display memory allows either 1 or 2 parameters, we have to account for whether it's 1 or whether it's 2 parameters, because if it's 1 parameter we're only printing 1 memory location. So this is what this part here does. It's very, very similar to the above in the fact that it takes the first element of the token and says, okay, check whether it's base 16 or base 10 and set what a variable called a result to whatever the parameter is, and then print out print out the contents. But so what have we got here? It's printing out the address, the hex, and the decimal. And so that prints out the hex, so the result 1 there, which is result 1 here, that's the memory, that's the actual memory location, so C000. Then we're printing out the contents of the memory location in the array, and we're printing out again, because the first time we print it out in hex here, and the second time we print it out in decimal here, and that's exactly what happens, because we did that there. So that line there, based upon that, this command here is translated to this code here and prints out that lot there. Okay, and if the number of parameters is greater than 2, i.e., then do this bit. All right, so it uses a variable called result 1 and result 2, and result 2 obviously takes the second parameter, and then we run a for loop which runs from result 1 to result 2 and increments the counter, and then just basically prints out exactly the same thing as this printed out, the only difference being that we're printing it out for each iteration of the loop. So it goes round and round and round and round
and that is shown by doing something like this, and then that's the first one, and then C00F, so it will count from C000 through to C00F and print out the contents. And that is pretty much all that the second iteration did. I created an interactive CLI with some ways to manipulate the pretend memory, the array, so that we could put hex values into that memory, and at the next phase we'll then start to take those hex values and interpret it into instructions and do something useful with those instructions.